say that's right actually. 2x transpose x theta equal 2x transpose y. Drop 2's. Okay. Theta equal x transpose y, x transpose x. Okay. Does this make sense? Now, x transpose x, what is that? What's the dimension? It's always a square, right? A square matrix. 1 over a square matrix. What was that?
N into n.
Yeah, that's n to n. That's a square. Okay. 1 over a square matrix. What do we call that? Inverse of a matrix. If a matrix is a square, 1 over that matrix becomes inverse of that matrix. So we can show this as basically x transpose x inverse x transpose y. Right? So this basically now is transpose y. Before I move, anyone that thinks that didn't make sense? Is that clear to everybody here? It's not clear. That's the time to say, hey, repeat. You want me to go over it again? Yes. Okay. So, do you agree with this concept with taking a derivation, and can you follow the derivation, right? So we reach to this term. This is equal to 0, correct? So we want to calculate theta. So we took this one the other side. We got rid of 2's. The theta becomes this term over this term. X transpose x, any matrix times itself, it provides a square matrix. The definition of the inverse of a matrix. If the matrix is a square, 1 over that matrix becomes the inverse of matrix. How do we show inverse of a matrix? To the power of -1. So basically, this is the same thing. I just rewrite it, as inverse of the matrix. Okay. So this theta star is the theta star that gives us this value. Okay. Now, you all, at least majority of you have worked with scikit-learn, right? Have you ever done linear regression? Yes. Fit a data set. Now, when you say data set fit, and it gives you the theta, that's the formula behind it. That's it. Oh. If you know the math behind this is linear regression. If you want right now code it on your machine, this is what you're going to code. What is X? X is my data set. Let's say you call it DF on your machine. DF, Pandas has transpose, right? Transpose, DF, basically dot, DF, transpose, dot that column Y. Inverse, we're right. And that's linear regression. You see the idea behind it, right? The math behind them is simple, as long as you be able to follow the structure and create it. Like that means that take the steps. How can I solve this? What formula can I use? Then see that if it's convex, is it concave? It gives you idea. Can I take a derivation, set it to 0? You follow that and you get to the theta that you want. And that's the end goal. To reach this theta. You have this theta, linear regression for any new data point. Let's say you want to predict Y test. X, you receive X test as a data, and you want to predict Y. So you will say Y hat test basically equal theta star transpose X test. That's it. And for any new data point that you receive, you do this multiplication, it gives you the predicted value. That makes sense?
Can you explain this?
After I solve, this is your model, basically. All you do, you want the theta. Because we know the definition of linear regression is that for any input, you multiply it linearly by this theta. There's no formula or anything, right? The theta is what you need. So now I get a new data point. X test means the X test is one record in a new data point that I have, or test data. And I want to see that, test my model to see that how good is this. So I multiply this data star by that one record and gives me Y test, Y hat test basically. Now I can compare this with my Y actual Y value. Does that make sense?
Yeah.
So now this is linear regression. And the answer that we reached is closed form solution. Because remember, the definition of closed form solution is that if you're able to take a derivation and set it to 0, that's solve for the parameter, that answer is a closed form solution. Now, if you go somewhere and someone tells you that, can you solve linear regression using normal equation? Okay, or closed form solution. That's the answer. Okay, that has two terms. Normal equation, closed form solution. I always say this story. So when I was a student here, I think it was my second internship I was applying. I applied for a company called Philips. And the guy that I was supposed to work for him, he came and on the pad asked me that code. It was like the first 10 minutes of the internship exam, whatever we call it. And he asked me about linear regression. Can you code linear regression? In his mind, I was supposed to do linear regression like a really sophisticated code. I wrote that. And he laughed and he was like, can you make it more complicated, like a solvable? It was like he didn't know that. And I was like, that's the answer. Anyway, we went and I figured that he didn't like my answer. So we finished the exam. No, I was like, he's not gonna answer. He called me back a couple of hours. I was like, actually, he was about, I know what's gonna happen. He's about to go to someone else and laugh and say that this guy gave me this answer. And I think someone told him that actually that's the answer. Right. So he called me back. I didn't do any, he didn't ask me any other question. He called me back and go, yeah, you have the internship. So some small things, it's like I really use, remember, someone tells you to solve a linear regression. I don't need a sophisticated code, I give you the answer. However, you need to know that, okay, this is, if linear regression was that simple, so what's the point, right? So there are some caveats, right? Now, who here can tell me that, what do you think is the caveat in this equation? There's something wrong with it. It works perfectly, but there's something in this equation that should capture your eye. Yes.
Yeah, make the inverse.
That's correct. First thing is that, okay, inverse of a matrix is OD3. That's the complexity of inverse. You know what to do is that on your machine, create a sample data set, using any libraries that you want, scikit-learn. Create a sample, it's like a normal data set, 10,000 records by, I don't know, by 100 columns. And do inverse on that. And time it, see how long this is gonna take. Then make it 100,000 records and time it. And you will see that your computer freezes, it doesn't give you any answer back. So inverse of the matrix, despite the fact it sounds simple, it's actually majority of computers are going to basically crash at some number of data records. So it's expensive. If you have a lots of data set, you don't do it. We always have a test, like a checkpoint in the code for linear regression. If size of the data set, for example, is more than 100,000 records, don't do closed form solution because it will take forever, either freeze. That also, depends on the computer that you have. The more computational power you have, the higher the number of records you can process, but at some point, still it will break. So one is that it's expensive. The other one is that, okay, this is a square matrix. The definition of inverse was that the square matrix is invertible if it's full rank. We haven't checked to see that if it's full rank, right? So you need to check here. This multiplication, x transpose x, which is a square matrix, is it full rank? If it's not full rank, then you cannot do an inverse. Then you cannot even solve that, right? So, expensive. X transpose x inverse should be full rank. Now, what was the definition of full rank?
Linearly independence is equal to number of.
But what's the equation? What you should check? The rank of a matrix.
Determinant not CSL.
No, those are all correct. Those are all ways that you calculate. Like, for example, if I want to know if a matrix is full rank, I can do eigenvalue decomposition. Look at all eigenvalues. If there's if there is any zero eigenvalues, is not full rank. No. But the other one is the definition of full rank matrix was that matrix X is full rank if rank of X was equal to exactly equal minimum of M and N, or N and D, let's say. N and the number of rows and records. Okay. If that's the case, it's full rank. Now, we want to check for this term, X transpose X, which is, that's our matrix, that multiplication, right? You want to calculate rank of X transpose X. Rank of A times B, what was the equation for it? I wrote four. Rank of A, the rank of multiplication is always less than equal rank of A and rank of B. So this should be always less than equal rank of A. That's right, minimum of rank of A and B. Minimum of rank of A and rank of B. Okay, so what is A here is X transpose. What is B here? X is X. Okay, so right here, X is. So rank of X transpose and rank of X. You're the same. Rank of X equal the rank of X transpose, right? So this basically, this is the same as that. So you don't need to calculate minimum of the same thing, right? So that means that this value should be less than equal minimum or basically rank of A, because rank of X. Again, rank of X transpose, the rank of multiplication is always by definition less than equal rank minimum of rank of first one and rank of second one. Rank of transpose is the same. Rank of X transpose and rank of X is the same thing. So I don't need to say this should be less than equal minimum of itself by itself, right? So this value should be less than equal rank of X or rank of X transpose because this is the same thing. Does it make sense? So now X transpose X, what is the dimension here?
Cross
N by D. This becomes D by D. X transpose becomes D by N. N by D becomes D by D, right? So this is D by D. Right? So the rank of a D by D matrix, basically, we are saying the rank of a D by D matrix should be always less than equal rank of X. Okay. Rank of N by D matrix. Does that make sense?
Yes.
What we are saying so far here. X transpose X is D by D. So basically we are saying that a rank of a D by D matrix should be less than equal rank of X. What is X? N by D matrix. Right? So now here, rank of a matrix is minimum basically of N and D, right? You're looking at the number of rows and number of columns, pick the minimum value. So here there are two scenarios. If N greater than D, then the rank of this term becomes D. Correct? If n is smaller than d, the rank becomes n. Okay. So rank of d by d is d. Okay, so here's this side of the equation, we have d. That side of the equation, we are saying that d is less than equal. There are two scenarios. One time you get d, one time you get n. D less than equal d makes sense, correct? So this one makes sense. D less than equal n. That doesn't make sense because here we said n is less than d. Right? So this one doesn't give you answer. We call this low rank. Let me go over this again. In order to prove this matrix is invertible, you need to prove its full rank. We know a full rank definition of full rank is that the rank of a matrix should be equal to minimum of n and d. That's a full rank. Also, we know rank of multiplication is always less than equal minimum of rank of individual. Rank of individual, because it's x transpose and x, they are the same. So we got rid of all of that and we just kept rank of x. So we say rank of x transpose x less than equal rank of x. X transpose x, x is n by d matrix. X transpose x is a d by d matrix. Rank of a d by d matrix is d. Okay, so this side, on the left side, you have a d, rank d, okay? Less than equal rank of x. X is n by d. Definition of rank is minimum of n and d, correct? So there are two scenarios here. Either n is greater than d, that means the rank of this matrix becomes d. In that scenario, d less than equal d, correct? Matrix is full rank. In the second scenario, we are saying that if n is less than d, then rank of x becomes n. Here we reach to d less than equal n. However, n is less than d, so that equation is not valid, correct? So that's called low rank matrix. Is not invertible. Now, let's understand this in a lame language. What's this n and d stands for? You have a data set. You want to see that can I solve it using closed form solution? You need to look at the number of records that you have, number of columns. N is number of records. These are how many columns you have. If you have more records, okay, than your columns, you can solve it. If you have more columns than records, you cannot solve it. That's what it tells you. So you put this test in your code, check the side dimension of the data. If you have more columns than records, I cannot do closed form solution because it's not full rank and it's low rank. Does that make sense? So this is closed form solution. This is the test that you need to do, in order to be able to solve it. Now, okay. This is an example of a closed form solution. But here, if it's not closed form solution, then what should we do? Let's see if I have an example first. Okay. So now we want to talk about this scenario where we don't have a closed form solution. So we are going to learn about something called the gradient descent. Or case G. Question? So we want to learn about something called gradient descent. Now, closed form solution is basically we always try to solve it, but you will see majority of the times it's not solvable. Because not everything has a perfect scenario and we need to be able to solve it using closed form solution. And there is a technique called gradient descent, which is an iterative approach. It's an iterative solver optimizer. So it's basically it's an optimizer. It's iterative. Now, gradient descent is, and you will see that it's basically we are using it almost in lots of algorithms. We will talk about why we are doing that. Now, the idea behind gradient descent before we talk about math is, let's actually emphasize this optimizer for convex function. So you have a convex function. Okay, I think the camera is working. So let's see. So we have a convex function, and we know we want to reach to this point, which is the gradient is 0. In closed form solution, we just simply could take a derivation, solve for that theta. If you cannot do that, that doesn't mean that you don't have a minimum point. You still have a minimum point that you want to reach. But that minimum point, you cannot reach to that by taking a derivation and setting to 0. You cannot solve it. So then there's a technique called gradient descent. So a gradient descent, it has actually other terms also, like a hill climbing. You heard that. Climbing, that's another concept. The whole idea is that, let's assume, let's start with the definition of hill climbing. Let's say you are going, camping, or you're just going to nature and you go on top of the mountain, right? And you go up, basically, and now at the end, your goal is to come all the way down, right? So if you look at a mountain, so this could be a mountain, right? Or the hill, basically, right? From different angles, it's supposed to be 3D or more than 3D dimension. You can reach to the bottom, right? So there are ways that you can come down, basically. It's like you're taking a small, when you go down, you just don't go straight down. You always have some ziggy-zaggy movements, right? So the whole idea here is also the same thing, that you want to go from one corner, maybe here, let's say there's a human standing here, or basically here, and you want to reach to here, And don't ask me why I go here, but the rule is that, for example, you go from here, 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 here. And if you want to ask why we don't move that way, it's just 2D. In 3D, actually, you move that way. Okay? The other example could be that, imagine I'm standing here, I have a basketball and toss it down. So how does the ball go down, basically? It bounces back between walls, right? That's the whole idea behind gradient descent, right? It's an iterative optimization technique that you're at somewhere up, and you want to reach to bottom here. And what you do is that you basically iteratively back and forth between left wall and right wall until you reach to this point. Okay. Now, I will open up this concept more. Just bear with me. And the math behind it is that this is theta, correct? This is j theta or f theta, whatever you want. At each time step, first time I'm here. Next time I'm here. Next time I'm here, right? At each time step, the location that I'm at has a corresponding theta and corresponding j theta, correct? So we will say that theta at time t, okay, is equal to theta at previous time, where I was before, okay, minus the learning rate times gradient of theta with respect to theta at time t minus 1. And I'm going to explain that. First, so anytime you hear the term gradient descent, that's the formula, okay? It's always like this, theta at time t equal theta at previous time minus, this is called learning rate. This is also the gradient of the function with respect to theta at the previous time. Now let's see what does it tell you. I'm here right now, then I go here. Okay. So at the current step here, I have an associated corresponding theta 0. Okay. Then I'm taking a step, I got to this point. theta at this point equal theta at this theta, and then you also have this j theta, right? You take a derivation of this function with respect to this theta, okay? And you update that. Each step, I take one step, basically I get here. Now I'm here, right? I have the value of theta, theta 1. Theta 1. Also, I have the function. I take a derivation of this function with respect to theta 1. What is the derivation of a function? The slope at this point. That's the derivation, right? So this is the derivation of j of theta with respect to theta 1. It's the derivation with respect to theta 0. And so on. Then I go to this point, take a derivation with respect to this one. Now, this derivation at this point, is it positive or negative? Positive. So, and here is negative, right? So you know that always on the right side, the gradient is always a positive value. On the left side, the gradient is negative value. Okay, so how is that going to help us? Your goal is to reach to this point, this theta star. Okay. This movement, this bouncing back, the whole idea behind it is that you are guiding the ball to reach to this theta. How? So first time I'm here, okay, I calculate the gradient of theta. Okay, the gradient is not 0. What does that mean? I haven't reached here because at this point you have a gradient of 0. So gradient is not 0. What's the value of, what's the sign of the gradient? It's positive. That I know I'm far, right? So what do you want to do? I want to reduce the value of theta. I want to move in this direction. Because the theta gradient is positive. How can I do that? I would say that theta minus the gradient of function with respect to that theta. Ignore that alpha we will talk about. Okay. So next time I'm here, the gradient is negative. That means I need to go this way. So look at this. Theta minus a negative becomes positive. So theta plus something. So you're increasing the value of theta. This bouncing back and forth happens to the point that you get here, the gradient is 0. That's your checkpoint. Every step you calculate the gradient. Is my gradient 0 or close to 0? That's the whole idea. We will talk about it. If yes, stop the learning. If not, you continue back and forth, plus minus, plus minus, plus minus. At some point, you will reach to the end of the ball. Does this make sense? Anyone wants me to go over it again? It's an important concept. We're going to use it often, basically. Yes.
So what's dictating our learning rate?
Okay, we will talk about that. Now, I haven't talked about what's learning rate first. Then we will talk about decay. So,
But we're taking the derivative with respect to theta t minus 1. What does that? Let's see theta t minus 1. T minus 1
this is the theta, right?
Yes.
T minus 1 is the time. So theta at, so t is the time. Okay. Let's say I start the learning. At time t equals 0, my theta, let's say I have 2 columns. I have one theta is 0.2 and another theta is 0.8 at time 2. This is a vector, correct? J of theta is a function, correct? Can I take a derivation of this with respect to that? Yes.
Yes.
So it gives me a vector, correct? This term is a vector. Let's say 0.05, 0.4. That's the gradient. In order to find theta for time 1, which the next theta that I should go to, you would say theta at time t equals 0, which is this, minus alpha times that. Alpha times that 0.05 and 0.4. This basically, this minus something times that, this minus something times that, and this becomes my new theta at next time step. Did that answer your question?
Theta 0, there is no t minus.
We will talk about that. Let's say the whole idea behind theta series is a random initialization. And you want to start, you don't have any value of theta, put it 0, whatever you want. In next iteration, next 2, 3 iteration, it automatically updates. Because if you put 1 million as your theta, your gradient is too large, next iteration theta goes down. That's the whole idea. But at each time stamp, next theta equal previous theta minus the gradient corresponding to that previous theta. Okay, times and alpha. Now we want to talk about what's this alpha. So if I want to go down the hill, alpha is a step that I'm taking. How big I take the steps. I could do it slowly, I could jump. When I toss the ball, I could toss it really heavy, bounce back really heavily, or just toss it slowly, right? What's the impact? So let's write this. Let's go alpha or learning. Right. If alpha is too large, very great answer, that is too large. Let's see what will happen. At each step, let's say my alpha is 10. My gradient is 0.05 and 0.4. 10 times that, right? This becomes 0.5, this becomes 4. The impact is negative. It actually has a really bad impact, right? So what will happen? I'm here, because my alpha steps are too large, I go down here. Okay, that might look good, but next step, I will go down here. What do you think will happen after this? You bounce back. This continue, basically this will repeat for a long time. So if your alpha learning rate is too large, basically it will slow your learning. It will produce high errors and so on. It's not good. You will see that your model is not learning with that you will wait for your code is running for so long and it doesn't produce a good result. That's because your alpha is too large. Now, what will happen if the alpha is too small? Correct. So if alpha is too small, that means, let's say, what's too small? 0.000001. Okay, and I'm going to talk about the values for alpha. Then your learning is going to be like this. And you can imagine how long it will take to get to the bottom of the hill. You know, sometimes it took too long, and you at some point, you basically code stops because there's always some stopping criteria. So, too slow, lower error, however, because in high alpha you jump from the point. In low alpha, really small alpha, basically, you finally will reach to the bottom. You finally will reach to the good point, but it takes too long. So your goal is that to select alpha to be optimal. Now, when we say alpha to be optimal, and before we talk about alpha being optimal, let's talk about values of alpha. Like, what are the common values for alpha? Like, how could we decide on values of alpha? So the whole idea behind is called hyperparameter tuning. Hyperparameter tuning. So in machine learning, deep learning, you will hear two terms: parameter tuning, hyperparameter tuning. Parameter tuning is when you tune the parameters of the model, like theta. That's the goal. That's parameter tuning. Anytime that you hear the term hyperparameter, that doesn't talk about models parameter. That talks about parameters like alpha. You know, the additional parameter. Alpha is not a parameter for your model. It's a parameter. We are using an optimization technique. Is parameter belonging to that optimization technique. Theta is the parameter for your model. Okay. So anytime you want to find alpha, you need to do hyperparameter tuning. Now, hyperparameter tuning is this new math behind. The whole idea is that you define set of basically alphas or the range of alphas, and you do something like binary search. Like I have a large alpha and I have a small alpha. I calculate the large and the small and something in between, and I decide which direction I need to go. Basically, you know, it's a binary search basically. So if someone says, "What is there any rule of thumb for values for alpha?" When you practice with it, yes, there are rule of thumb. If I want to select alpha based on my experience, I always pick alpha something between 0.01 and 0.001. I don't go beyond that, or I don't go basically higher value of alpha. But that doesn't mean that that's the best answer. No, based on the data that I work with, that's the answer. Your data might be different. Think about the problem this way. There is a data set that you have. It's easy to learn. It's not difficult. In that scenario, I pick a normal alpha. Alpha is 0.01. But there is another data set that I have. It's really difficult to learn. You know, it needs a lot of iteration. Then you want to pick a smaller alpha. You want to take a smaller steps. You know. So that's if your data is problem is hard to learn, pick smaller alpha. If it's easy to learn, take a larger alpha. You know, and then you do a comparison. Question?
Yeah, can we iteratively decrease the alpha?
We will talk about it. Okay. So, any other question before make sense? So now your friends they asked two questions. So the term that you mentioned, and he mentioned, is called weight decaying, or decaying basically concept. Now, there is a concept called decaying, and decaying basically means that, you know, when you start the algorithm, at the beginning of the problem, when I'm standing here, I know I could go much faster. But as I go down, could I slowly decrease the value of alpha? That's called decaying problem. Okay, so decaying. Now we use this decaying with weight decaying, parameter tuning, hyperparameter tuning, decaying. Anything that comes basically decaying, the idea behind it is the same. That means that as time goes, you reduce the value. So again, that means that at the beginning I'm here, I take a larger alpha. At some point when I get here, my alpha starts to become smaller. That becomes a decaying problem. Now, there are a couple of formulas for that. One of them, which Robinson, Monroe. So that alpha time t equal some sigma t plus tau. Okay. So alpha at each time step, because you have this sigma is going to be some value, for example, 0.01. And there is a t, let's say here, this is also 0. Maybe you could put this 0.02. It even could be 0.01, same thing. Because there is at each step on the denominator, you're adding something to it, right? So as time goes, this becomes larger. And the value of alpha becomes smaller gradually. This one is specifically called Robinson-Monroe. Okay, it's a weight decaying. But again, any function that you can think of that as time goes gives you a smaller value, it could be a decaying function. It doesn't necessarily need to be something that is already developed. Any function that you can come up with, somehow, you publish a paper and you want to decay your weights based on the, I don't know, sinusic basically form, or or whatever. So it doesn't necessarily need to be proven. Now, let's so we talked about gradient descent. We wrote down the theta of it, but we want to, yes. This one?
Yeah.
Alpha time t equal some initial value, 0.01, for example. This is constant. This is also a constant. You decide at the beginning. At each time stamp, you divide this value over t plus this value. At each time step, t increases, time step 1, 2, 3, right? So this divided by something that is increasing slowly gives you a smaller value of alpha. So you're decaying the value.
What is that T? It's
T is time. Time. Sorry, T is here time. That's tau. This is T. That's tau. This one is tau. This is T.
What is that's time for like the constant value?
This one is T. T has a time. And this is also time. Alpha at each time.
How do we derive to the tau? Like what's the logic there?
It's a constant number. You decide. You decide. It's a constant number. Imagine sigma at the beginning I pick 10. Depending on what's 10, you're going to think that how large you want your initial alpha to be. If this is 10, if I pick this 0.1, initially that almost becomes 100. Right? Maybe I don't want that, so I make this larger. But depending on how do you want to be the initial alpha and where you want to go, you select these values. If you pick this as twice large as that is, you're gradually basically, it's basically quadratically almost going there. Right? So you decide on those parameters. Those are themselves are hyperparameter also. You decide. You will see that we have so many hyperparameters. The whole field, same question, you're always going to end up getting a different answer because the hyperparameter you pick is different. So if your code and your friend give the same answer, we know you're cheated because there's no way two people exactly pick same hyperparameter everything, right? So that's the whole idea behind this type of coding. Your answers are different. So here also imagine these are hyperparameters. You decide in your problem in the domain that maybe you either have a domain knowledge. That means that there was other group in your company, they work on this project, they already proved these two values are good. You're going to use them. Or there are a couple of papers already published. You're going to use from those papers. Or nothing, you're just going, by chance. You just pick values and randomly evaluate those.
Yes, can you put alpha t minus 1 instead of sigma?
Alpha t minus 1?
Instead of sigma.
Yeah.
You can.
Well, yeah, I told you any formula that you come up with decays for you, that works. Okay. Now, gradient descent, we want to write it down. Okay, so like it's going to do the pseudo code, so for gradient descent. Now, step 1. I'm not going to write a step anymore, but just step means 1, 2 means a step 1 step. You need to randomly initialize theta. Okay. At first step in gradient descent, you need to randomly initialize some value of theta. What's the meaning of that? If you're looking at this ball, at the beginning, where are you standing? You don't know. You randomly close your eyes, select some theta. That's your initial starting point. Right? That even your theta might be here at the beginning. Doesn't necessarily need to be there. It's the random initialization. So theta. So theta has d dimension at time t equals 0. So you randomly initialize some theta. At step 2, now we want to start moving, bouncing back and forth, but how much for how long? This is a question you need to think about if you want to create a code. How long this code should bounce back and forth? But is there a guarantee that your code will reach there? No. Problems could be difficult. So you need to have a for loop. You know, you always will write for t from 1 until convergence. Okay, we're going to talk about convergence. Okay. Now, convergence is a condition that we are going to define. We're going to say that, okay, you know, my goal is to reach the derivation at 0. But if I didn't reach the derivation of 0 and any of this bulletin or tick marks was marked, you know, condition was met, stop the learning. So you're going to write so many conditions. It's not just one. Because think about it, with a small data set that is cheap to run, for large data set, company properties and stuff like that, you can't just run a code and when someone asks you what's your answer, I'm waiting for it to run. No one will wait for you to run your code. You need to quickly be able to get answers, you know? So until convergence, what's the next step? 2.1. So we know for theta at time t equal theta at t minus 1 times the learning rate divided times that gradient, right? So now t minus 1 should be t minus 1 on the derivation. This mean, or actually this class is hot. I hate teaching in the snows. Nothing works. The camera doesn't work, the heat doesn't work. You don't have a control on anything in there. You need to send a message and you will later watch the video for today's class when you will laugh. It's like a 5 second goes for 10 seconds, 5 seconds, 10 seconds. And my last communication with the department was like, we don't have any class to change, but they have fixed it. Like it was yesterday, they have fixed it. And there's a third time they say they have fixed it.
I came before the class and then it works well.
It
That's
works.
right. And then
They wait for 10 seconds and they say it marked, converged, and then it doesn't work. Anyway, so actually let's clarify this. So we were J of theta was x theta minus y, correct? That was J of theta.
T minus 1.
Yes, I see. Probably T minus 1. Minus 1. I actually says that, so it doesn't matter. But yeah, that was J of theta, correct? So in closed form solution, we took a derivation, set it to 0, solve for it. In gradient descent, you cannot set it to 0, but you can still take a derivation of this, right? So we already saw that you can simplify this and you reach to theta transpose x transpose x theta minus 2 theta transpose x transpose y is y transpose y, correct? And you wanted to take a derivation of this with respect to theta. The only difference here is that you don't set it equal to 0. Okay, so this basically gave us 2 theta to x transpose x theta minus 2 x transpose y. Okay. If you simplify this, so we have 2x transpose basically times x theta minus y. Okay. Get rid of 2. Let's always get rid of 2. The reason we have 2 is that, you know, so when you want to solve numerically, you actually don't get rid of 2, but when you want to prove, the 2 doesn't do anything, it's just a scaling factor. Now, this is the derivation, correct? This is the derivation. That means this term, correct? That's exactly the same thing, the derivation, I didn't set it to 0. Now, at each timestamp, you will calculate theta at time t equal to theta at time t minus 1 minus learning rate times the gradient, and this is the gradient, which is x transpose x theta minus 1. X theta t minus time t minus 1. Does that make sense? No? This, for gradient descent, you need to take a gradient, right? One time deviation. Here, that's one time deviation. I get rid of 2. You can keep the 2, doesn't matter. Doesn't make sense, just keep the 2. We're going to basically replace that term here. Now, what do you think this is telling you? This gradient term. What do you think? What do you see here in this equation? Was that more or less converge to 0? No, but look at the values. What do you see?
Theta minus y.
What's that? X theta. Right.
The difference now, y.
But what do you call x theta?
Residual.
Yeah, that's a residual. But why do you y hat? Y hat minus y.
Yeah.
The residual, correct? Residual times input. That's the definition of gradient. How much residual you have times the input that gives you the gradient. So at each time, theta minus learning rate times gradient, which you can calculate this way. You update basically your theta. Now, okay, so you calculate J of theta at time t, okay. Which is basically, let's say we go with this, x theta t minus y. No, I'm too. Calculate. So at each time, when you update the theta in this line 2.1, we did update the theta, correct? We have a new value at time t. We added value at 20 minus 1. We did minus the gradient. It gave us a new theta, correct? Look at this again. We were here. We got here now, correct? That gives us a new theta, theta at time t. Theta at time t, it has corresponding j of theta, correct? Which is the error, the cost function, right? So I'm saving it. We just put it in a value, put it in a variable because we want to do some tests. 2.3, we check for convergence. Now we're going to talk about what is convergence. So when we move, we need to have some condition that you check. If you met any of this condition, your code should break. Okay. That's called convergence. Now, one way for convergence is that the gradient of theta with respect to theta at time t becomes 0. You reach to the bottom point, correct? That's one way of defining convergence. However, that's not always the case. Majority of times, it's actually not the case. Now, if let's think about this outside of the concept of machine learning. You're a programmer. You're writing a program that has a for loop. What's the easiest way you can stop it? Like what would come to your mind? Yeah, no, but how? Like, what should be a condition to break?
Theta t is equal to theta t.
Easiest way is what he said. Number of iterations. I define like a 5,000 step. My for loop, if past 5,000, break. So step 1, you define a max iteration. Okay. If t equal max iteration, you break the code basically. Okay. 3, you were going somewhere with what you were saying.
30 is equals to theta t minus.
Correct. And if theta at 2 time step, my updated theta and my previous theta are almost the same, right? How could you compare two theta and theta t and theta t minus 4 are a vector? How would you compare to see they are the same? Two vectors, how do you check to see that if they're the same? How do you calculate the difference between two vectors? L2 norm, right? Calculate an L2 norm. Theta at time t minus theta at time t minus 1. Okay, to the power of 2. If is really small, epsilon, it's not going to go to 0. Okay? If it's really a small, you define epsilon. Epsilon, let's say, as an example, is 0.0001. Okay, then break. Or these are again, you don't need to check for all of this. These are idea to give you idea of how many ways you can check for convergence. What else can come to your mind outside of this? If you want to check at each step, what do you think you can check to see that if you can stop? No, upward now. I'm going to tell you why now. What else? One was theta. What else do you see here that you could check? Yeah, j of theta, right? If j of theta at time t minus j of theta at time t minus 1, absolute value of that is also, let's say, less than some epsilon. Great. There's so many ways you can write these to check for convergence. Okay. The whole idea is that the definition of convergence is that in some consecutive iteration, your learning is slow. You are not learning much. Okay. Now, to answer your point that what if the theta increased? Well, there's a chance theta increases if your learning rate is large. That doesn't mean that you're not going to go back again. That's not increase in theta doesn't mean that you need to stop. Why? Because when you want to check if your theta increases, you will still do a norm 2. You get a positive value. But if the difference is small, then that's a difference. Or if j of theta is one of them is really large, the other one really small, that means you went up again, then this is going to be really larger than that. So you're not basically breaking the code.
Then we decrease the answer.
No, the code will, the idea of gradient is saying that if you go up at some point, it will come back. But if your learning rate is too large, that bouncing back and forth is going to take forever. Then you will reach to most likely the max iteration point. That doesn't make sense.
If you're bouncing up, doesn't it mean that your learning rates are largely huge difference?
Yeah, but the thing is that you don't know it at the beginning when you're training, right? You don't know what's large learning rate. You train, then you're looking at your cost, and then you understand that something is happening. Now, imagine at each time step, you can store the value of cost corresponding to that time step. And that's called cost analysis. We will talk about this later. You can draw cost based on time. The idea is that cost should decrease, goes towards 0 as time increases. If you see a curve like this, the cost is going back. That means a couple of things. One is overfitting. The other one is large value of theta bouncing back. So there are always some ways that you need to do cost analysis to understand that the cost is going up. But this depending on what type of data we are looking at, is it trained data, validation data, test data, has a different meaning also. Yes.
How can we say that we're overfitting if the cost is increasing?
So this is your validation data. This is my training data. Okay. When you train, you normally have 3 data sets: training, validation, testing. Training data is the data that you use actively for finding the value of theta. Validation data is the data that you use for monitoring. How good is this data that I'm learning? Imagine I'm learning. Oh, okay, validation is also going down. All of a sudden, validation goes up. That means at this point, your model overfitting. Training goes towards zero, validation goes up. That's correct. So. So now, this is the general form of gradient descent. If you check for conversions. If you converge, you break. Otherwise, this loop basically continues. Okay. Now, there is one downside with gradient descent. Okay. And think about what we are doing here. At each time stamp, we are calculating this value, x, which is your data, times this, correct? What if I have 10 million records? What if I have 100 million records? What if I have 1 million records? This is a slope. The number 2.1 is a slope, right? Gradient descent by default at each time, at which time stamp 2.1, you need to calculate the gradient of its function with respect to theta for full data set. So if your data set is large, that operation is costly. Does that make sense? If I have a large 1 million, 10 million data set size, multiplication of 10 million records by 10 million by D column minus 10 million, that's making it really a slow training, right? So we have another version of gradient descent, which is called stochastic gradient descent. SGE. Okay. So there are different type of gradient descent overall. Overall, remember this: gradient descent itself is not useful anymore. No one uses gradient descent itself. You're always using some version of gradient descent, because when the gradient descent paper came out, the concept of data set being large wasn't something. But now it's not useful anymore. So you need to use different version of gradient descent. You know? So the first one is a stochastic gradient descent. A stochastic gradient, everything is the same. All formula are the same. There is one tweak. In a stochastic gradient descent, basically, at time 2.1, bulletin 2.1, which we wanted to calculate. Let me actually get some empty space here. 2.1, which we wanted to calculate this value. Actually, write this as x transpose x theta minus y, right? Rather than doing this for all your data, you have one point behind this. Let's call it 2.0, and that's called sampling. What does that mean? Rather than I calculate the gradient for all data points, I sample from my data set, maybe 1,000 records, and I only calculate the gradient for that 1,000 record. So you sample and you call it X sample, and you have also Y sample, where sample size is much, much less than your data set size. Okay, it's like you decide now, depending on how much computational power your machine has. So this becomes X sample. This becomes X sample. It's also sample. Rather than using all your data, you just use a sample. Now, I might bring this question to your mind. Okay, why should that work? I'm not using all my data. Why? I mean, basically losing information. No, you're not losing information. The whole idea of gradient descent is that you back and forth in what calculating the gradients, right? If I sample randomly from a data and I pick the gradient is not about the size, it's about the direction of moving. sample gives you, it tells you the same thing, go left or right, until you reach to the minimum point. You know, if you use all your data, your gradient size are more accurate, but it takes much longer time to calculate that gradient. If you sample, your gradients are smaller, the smaller movements, but it's converging much faster than taking all data, gradient for all data. So stochastic gradient descent is 10 times faster than gradients. It gives you the same answer, sometimes better answer. Because gradient descent, you know, sometimes because of the size of gradients, your model might have a bigger jumps. So a stochastic gradient descent gives you a better answer than gradient descent. And if someone asks me that, can you describe why? Because gradient descent is not about the size of the gradient, it's about the direction of movement. And doesn't matter, sample or full data, it gives you direction. There are some values for how much you jump, but still it's faster to take a smaller, but much more, you know, think about it, it's better to take much more smaller steps than a couple of large steps, but in a slow, basically, pace. So, yes.
There's a possibility that due to sampling, the data might be biased also sometimes. Like it has picked up the points which are similar.
No, so that's it is. There are sampling techniques. When you sample, to answer that, if I have a data set, you always shuffle your data. Always shuffle your data. Because we have different bias concepts, sampling bias, environmental bias. So there are so many bias concepts that you come through in a study. Sampling bias is the one that you, as data scientists, you always deal with. If you have this data set, should I pick from the top of the data set or center or bottom? No, you should randomly sample. If I have a data set, you're starting your project. I have a project, I have 1 million records. First thing is that you need to separate training, development or validation, and test data. That means if I have a data, we will talk about it. I separate them into 3 buckets. How do you separate it? I first shuffle the data, and then I randomly sample, blind sampling, basically. In that scenario, you shouldn't have any bias in sampling. If there's a bias in sampling, that's in sampling. If there is any bias in the data, that means your whole data set is biased because of the concept of sampling. So, does the stochastic gradient descent make sense? Now, you will hear the terms online gradient descent, batch gradient descent. They're all the same thing. The sampling is different. Online gradient descent means anytime you hear the term online means one data point at a time. So in online sample, you get one sample, update, one sample, update, one sample. Because you want to do it much faster, like cell phone type of thing, streaming data. Batch gradient descent, it has some batch concept behind it, which we will talk about that later on neural network. So.
Stochastic gradient descent, while calculating convergence, the point that you have given, it's a theta minus a theta minus t minus 1. So here what theta do you use? Do I use like
G theta t minus G theta t minus 1. Theta time t minus theta time t minus
1. Yeah, makes sense.
Yeah. Time means every time you update the value of theta, this is a time, this is the next time, this is a time, this is the next time. It's just time means the movement. If time is confusing, you can use index. In the for loop, I wrote for t. No, I wrote for t from 1. T is that time. So that's now. So this is linear regression, the basic of linear regression. Just there are 2 ways you can solve it. First solution gradients, and we learned about gradients. Now, we want to talk about the problems that linear regression has, and then break down the linear regression in different types of linear regression. But what we also find is just a general form of linear regression. Now, I wish we have so many things in AI. add some sort of whiteboard that would explain itself. Very nice. So, limitations. Now, we know that y hat basically equal theta x, right? X theta, sorry. X theta. And y hat phi for one data point is theta transpose xi. That's for full data set, that's for one data. So let's say this is x1, this is 1. I'm just plotting it for 2D. We only have one column and we have a y, which is the target, and we have one column, basically one feature. So let's say this is the data that we have. How do you think the linear regression, the linear regression at the end is a line, right? The line that goes through the data. Where do you think that line goes through? Through the center of the data. Where is the starting point for that? And the center, right? The 0. So that's theta transpose xi, correct? That's linear regression. Now, what if I have this data? Where do you draw that line? Linear regression line.
It shouldn't go to the center of the view, right? Like it should be at the center of the
Line is always goes through the center, right? So if you have a data set like that and you saw linear regression, any of these could be your data, could be your linear regression line.
why
Yeah, but so you see, that's the first limitation of linear regression.